All right, so here's our game plan. We're going to start with the absolute basics, then get into the nitty-gritty of what really happens with soil pressure. From there, we'll tackle what happens when loads get a little wobbly, and then we'll run through a real-world design example before we wrap it all up with the final safety checks that make sure a building stands tall and proud.
Okay, first things first. Before we can even think about designing one of these things, we've got to understand its fundamental job. I mean, what is a footing really for?
You know, in a perfect world, the concept is beautifully simple. A footing is basically like a snowshoe for a building. It takes this huge, concentrated force coming down from a column and spreads it out over a much bigger area. This way, the soil underneath can actually handle the weight without just giving up. The dream is to have this perfectly uniform pressure.
But, of course, the real world is always a little more complicated, isn't it? That idea of perfectly even pressure is a really convenient assumption for designers, but it's not actually what's happening underground. The type of soil you're building on, well, that changes everything.
And this is where things get really interesting, the gap between theory and reality. For our calculations, we often assume the pressure is uniform because, honestly, it just makes the math way easier. But knowing how different soils actually behave is the secret sauce. It's what lets engineers build in the right safety margins to create structures that are genuinely strong.
Okay, so check this out. On the left, you see our ideal design assumption, that nice flat line. But look at what's happening on the right. This is what happens in cohesive soils, like clay. The footing actually deflects just a tiny bit in the middle, which causes the pressure to get higher at the edges and a little lower in the center.
Now let's completely switch up the soil. On the left is that clay we just talked about, but on the right, that's what happens in cohesionless soil, like sand. With sand, the particles tend to shift away from the edges, which means the pressure is actually greatest right under the column, and then it fades out toward the sides. I mean, think about it. Two different soils, two completely opposite pressure profiles. Wild, right?
All right, so let's add another layer of real-world messiness to our puzzle. Columns don't just push straight down. They also have to fight against forces that are trying to bend them. And that totally changes the game for the footing down below.
Yeah, see, footings rarely get to just deal with a simple downward push. You've got forces like wind or earthquakes that create what engineers call a moment. You can just think of it as a twisting force at the bottom of the column that's basically trying to make the whole footing tilt over.
So to figure all this out, engineers use this really clever equation. The first part, P over A, that's our simple uniform pressure we saw earlier, just the total load spread over the area. But the second part, MC over I, that's what accounts for the tilting moment. It adds pressure to one side of the footing and subtracts it from the other. You put them together and bang, you get the real lopsided pressure distribution.
This whole thing boils down to a super important idea called eccentricity. It's really just a simple measure of how far off-center the total force is acting. I love this pizza box analogy. If you hold a pizza box right in the middle, it's perfectly balanced. But the second you hold it by the edge, it wants to flip and tilt, right? That's eccentricity in action.
And this eccentricity, it has a magic number, 1/6 of the footing's length, or L over 6. If your eccentricity is less than that threshold, the entire bottom of the footing is still pushing down on the soil. But the moment you cross that line, part of the footing can actually start to lift off the ground, which means you get zero pressure on that side.
And this visual just nails it, doesn't it? On the left, with just a little eccentricity, you get this stable trapezoid of pressure. But on the right, once you've gone past that L over 6 limit, the pressure becomes a triangle. That point of zero pressure on the far left of the triangle means that edge of the footing is right on the verge of lifting up. And that's a huge stability concern for any designer.
Okay, theory is great, but let's get our hands dirty. Let's walk through a real example and see how we put all this stuff together to design a safe footing that's got an eccentric load.
First up, we've got our dead load. This is the weight that never changes. The concrete, the steel, all the permanent parts of the building. In our case, that's 900 kilonewtons.
Next, we add the live load. This is all the variable stuff. People walking around, furniture, snow on the roof. Here, we're looking at 450 kilonewtons. And finally, we have that tilting force we were talking about, the service moment. It's coming in at 150 kilonewton meters. These three numbers are everything we need to get started.
All right, let's put these numbers to work. The first thing we've got to do is figure out how big the footing needs to be. So, based on the loads and what we know the soil can handle, the engineer has sized a footing at 3.5 by 2.5 meters. Now we plug everything into our pressure formula to see what we get. And yep, it confirms that uneven pressure. One side is pushing down at 183.7 kilopascals, while the other is way down at 124.7. The key here is making sure that even that highest pressure is still safely below what the soil can take.
Now for a really crucial safety step. Up to this point, we've been using service loads, which are like the day-to-day forces. But to design the footing itself, we have to plan for a worst-case scenario. We do this by applying safety factors to create what we call ultimate loads. The best way to think about it is you're designing for the biggest storm imaginable, not just an average Tuesday. And as you can see, these ultimate pressures are way higher, 245 and 166 kilopascals. These are the numbers we use to make sure the concrete itself doesn't actually break.
Okay, so we've got a footing that's big enough so the ground underneath it won't fail. We're good, right? Well, hold on, we're not done yet. Now we have to turn our attention to the footing itself and make sure the reinforced concrete is strong enough to handle these pressures. This really is the final and maybe most important question. The soil is pushing back up on the footing, and all that upward pressure can cause the concrete to fail in a couple of different ways. We absolutely have to check for both.
The first check is for something called punching shear. The best way to picture this is to imagine the column trying to punch a hole straight through the footing, like a fist going through cardboard. The calculation here is comparing two things. First, the demand, which is the upward force from the soil trying to make that punch happen. It's about 1,800 kilonewtons. Then, it calculates the concrete's capacity, or its strength to resist it, which is over 2,400 kilonewtons. Since our capacity is way higher than the demand, we pass. The footing is safe from punching shear.
The second and final check is for beam shear. This time, think of the parts of the footing that are sticking out from the side of the column. The upward pressure from the soil could try to snap them right off, kind of like breaking a shelf off a wall. So again, we calculate the shearing force, the demand, which is about 567 kilonewtons. Then we calculate the footing's ability to resist that crack, its capacity, which comes out to 828 kilonewtons. And once again, because our capacity is bigger than the demand, we are safe. The footing is strong enough.
So, there we have it. Our footing won't sink into the ground, it's thick enough that it won't get punched through, and it won't crack under the load. But we know concrete is great when you squeeze it, but not so great when you stretch it. So what's actually given it the strength to handle all this bending? Well, the answer is hidden inside, a carefully designed grid of steel reinforcement. But that's a whole other fascinating story for next time.